The problem we are tackling is trying to figure out how to train different reinforcement learning models to perform effectively on different Atari environments. These Atari environments have a discrete action space, so intuitively reinforcement learning algorithms should adapt well. We'll use three environments for our testing: Basic Math, Space Invaders, and Pac-Man. The reasoning behind using these three is due to their varying levels of complexity and different success metrics while maintaining a discrete action space. With this approach, we can see if these models generalize well through the differences in performance evaluation across these environments. This is important because these environments are good benchmarks for testing reinforcement learning algorithms, so we can optimize algorithm selection for discrete action spaces, and this can lead to improving our understanding of what different algorithms to optimize, what we select for future problems down the road, and what learns faster, requires less computational power, and performs better overall in diverse scenarios. Our hypothesis is that deep Q learning will outperform proximal policy optimization in these environments because DQN is specifically designed for tasks with discrete action spaces, making it an ideal candidate for Atari-style games. While PPO is also very suited for tasks with discrete action spaces, we believe DQN will outperform it simply because the value function estimation is simpler, and there is a stronger direct correlation between an action and the points it receives versus PPO, which requires a lot more trial and error.
In all three environments, we trained both algorithms for 10 million time steps using their stable baselines implementations. Performance was assessed every 200,000 time steps based on how well agents adapted to the discrete challenges of each game, testing our hypothesis that DQN would excel due to its design for discrete action spaces. To make the training process more efficient, we used pre-processing methods sourced from the papers referenced in our write-up. The first one applied is component-wise max pooling. Some Atari sprites are only loaded in every other frame, so we take the component-wise max of 2 consecutive frames to ensure all sprites are accounted for. We then apply frame skipping. Because Atari games are fast-paced, not every frame provides meaningful changes. Instead, the agent only observes every fourth frame, drastically reducing the computational load without sacrificing any critical transitions. Frame stacking is then used to provide temporal context. This is taking 4 consecutive frames, which in our case means 4 frames that are not skipped, and treating them as one state. This allows the model to infer things, such as the bolt trajectory in Space Invaders. For PPO, besides training on a single environment, we were also able to train on vectorized environments, which allowed us to train 8 instances of the game simultaneously. This reduced training time from about 10 hours to only 3 to 5. However, due to memory constraints, we couldn't do the same for DQN, so its training took about 7 hours per environment. This highlights an advantage for PPO, being that it's better suited for parallelization than DQN.
DQN consistently outperforms CPO in terms of average and peak reward. While DQN may exhibit higher variance, its ability to efficiently explore the action space and focus on high reward strategies proves advantageous. Sometimes it makes large steps in the wrong direction, causing large spikes in episode length and dips in reward. PPO, constrained by its policy-based approach in clipping, struggles to match DQN's performance, particularly in environments requiring precise action sequences. While the environments differ in their scoring systems, we can still analyze the convergence behaviors of DQ and PPO. In Pac-Man, DQN converges significantly faster in PPO, reaching a stable performance level of around 2 million time steps, compared to PPO's 3 to 4 million time steps. Similarly, in Space Invaders, DQN converges earlier at 1.5 to 2 million time steps, while PPO requires 3 million time steps. DQN's stronger correlation between episode length and reward indicates a more efficient strategy of eliminating invaders to score points. In the basic math environment, this disparity is even more pronounced. DQN converges at around 5 million time steps, solving 8 out of 10 questions in the basic math environment. In contrast, the PPO model struggles to converge to a policy capable of solving more than 2 out of 10 problems, even after 10 million time steps. These findings reinforce our hypothesis that DQN's value-based approach and efficient exploration strategies make it more suitable for tasks requiring precise actions and optimal decision making. Key takeaways. The DQN outperforms PPO in singular environments. While vectorization sped up PPO training, it didn't actually expose the model to any more data when compared to its training on a single environment, leading to similar performance results. One next step would be to modify rewards. For example, in the Pac-Man environment, the agent focuses on eating ghosts instead of eating pellets and beating the game due to the rewards for eating ghosts being very high. This may also be because of the lack of training or exploration.